Welcome to this session. It's called Beyond Machine Boundaries, and we want to share some, let's say, practical experiences we have with, power-based systems using memory disaggregation. So my name is Felix Eberhardt, and with me are Andreas Grapentin and Tobias Zagorny, who will also have a share in this presentation. And we are all, affiliated with. We are all affiliated with the Hasso Plattner Institute, and let me just 1 minute talk about where we are coming from. We are from the Hasso Plattner Institute. This is located in Potsdam. This is just a little south and west of Berlin, which you can see on the map there. And more specifically, we are from the Operating Systems and Middleware group led by Professor Andreas Polze. And in our group, let's say, two main research areas are, so we are interested in small systems and big systems. So small systems like, in embedded or in IoT, there we focus on real-time fault tolerance and security. There are two big projects. One is centered around telemedicine with the Charité hospital, and the other are projects with the German railway, Deutsche Bahn. But that aside, the other part of the research group does research on these big systems like server systems, data center, and all that stuff, where we have three major topics. One is energy-aware computing, the others is accelerators. There we look into FPGAs and GPUs, accelerating all different kinds of workloads. And the third one is memory subsystem, and all technology centered around that. And their one topic is disaggregation, and this is what we will be talking about today. Okay, so I want to start with a little motivation and present you some technologies used for disaggregation. Concretely, these are coherent interconnects. Then I'll present you ThymesisFlow, which our prototype is based upon, and then we continue with some research questions and areas, and we want to present you some practical projects we've done with our prototype. All right. So first, let me say a few words about resource disaggregation and why this is actually a very good thing to have. So let's say we are in a data center, and essentially our task as a data center operator is we have workloads, as seen here on the upper right corner. We have different workloads with different resource needs. So for example, workload A is a machine learning workload, needs a lot of accelerators, a bit of memory, and some compute. Workload B, for example, is an in-memory database with, let's say, some compute needs and a lot of main memory needs. And then we have a workload C, which is a batch workload with a very small compute, very small memory needs. And I mean, these needs do not have to be static and don't have to be defined from the start. They could change over the execution of the workload, right? The workload could have different phases with different needs. And so how do we map that to our server infrastructure, where at least now we have, if you look down here, we have servers with aggregated resources. For example, one server has one block of accelerators, one block of memory, one block of compute. So if we could have like resource pools where we don't have them aggregated in servers, but aggregated or disaggregated into homogeneous pools, we could carve out virtual machines and be more flexible, have better utilization, fewer stranded resources. Now, to have resource pools, you need to have very low latency, high bandwidth interconnects and have a very reliable connection. And probably this is hard to achieve, but at least we could think about doing that to some extent with main memory. And by the way, this is at least announced as a product in Power 10 and it's called their Memory Inception. So this could probably be a reality soon, right? To actually build such a machine or such a, let's say, memory cluster, what we basically need are coherent interconnects. And I mean, coherent interconnects are also good for other things. So for example, attaching a FPGA card or GPUs much closer to the or have a tighter integration of GPUs and FPGAs into the system, because with these coherent interconnects, you basically change the way you interact with this accelerator, coming from a, let's say, push interaction where the host has to push the data to the card in order to process it and then get the result back, to a pull-based interaction where the host can say or start the execution on the accelerator card, and the accelerator can pull the needed data it needs for the processing. So we do not need to copy data, but we can share virtual addresses. So this is actually very interesting. And I think in the introduction of Alan Kendall, you saw that with this IC922 and this NVLink, these machines, they were quite successful. So yeah, there are certain points. And there are several approaches for coherent interconnects. There's CXL, we heard about it. There's Gen Z, there's also OpenCAPI, and on OpenCAPI, our prototype is based. With these coherent interconnects, we have different modes of integration. This is true for OpenCAPI, and this is, by the way, also true for CXL. So to a certain degree, these two, let's say, technologies are interchangeable. They have two, let's say, major modes. One is a memory mode, wherein with the memory mode, attached card is seen by the system as, let's say, another memory controller. So it can offer physical memory addresses to the operating system and handle that. The other one is that the card is in the accelerator mode. There it can access the main memory of the system and can do that in a coherent fashion. Meaning, for example, if CPU core 11 here has loaded a data item in its cache as a cache line, and the FPGA card wants to access that same data item as well, it will not go to the main memory, but to the cache and receive the most up-to-date version of that data item. And now so in this setup, we basically combine the two modes. On the one hand, we have an FPGA card in this accelerator mode and a process spawned on the server which allocates memory and, let's say, share it with this FPGA card. On the other system, we configure this FPGA card to let's say, redirect load and store operations from a CPU core via the network to the other FPGA card, which then redirects it to the memory we allocated. So in this sense, we could say that we attach memory from server 2 to server 1. We base the prototype on ThymesisFlow. This is an open source project released under the OpenCAPI consortium. And when you have, so you can check it out and also, build such a machine or such a setup for yourself, which is very good. And once we discovered that ThymesisFlow was released, we nearly instantly got in touch with the guys who built ThymesisFlow, and we were also in the process of, extending our local data center. So we could have, so we could think about, getting Power 9 machines and FPGAs, and that's what we did. And we tried to get ThymesisFlow up and running. So first, let me give some credits. We did start a project with IBM Research Europe, the Next Generation Systems Group, and these were also the guys who developed ThymesisFlow. So this is Christian, Mikel, and Panos. And from our group, I'm also not alone. Andreas Grapentin, who is in this call as well, and Lukas Wenzel, Sven Köhler, and Max Blaut. We are currently working more or less on this disaggregation topic. And for the collaboration with IBM, we chose that a promising workload could be an in-memory database. We use a database which we developed here at HPI. This is called Hyrise. It's also open source. You can get it on GitHub. And here I just want to quickly give also credit to the main maintainers of Hyrise, Jan Kosman, Markus Dresler, Martin Borsi, and Stefan Hafprop. And so for memory disaggregation, in-memory databases could be a good fit as a use case because they, on the one hand, have a very large memory footprint. On the other hand, quite different data structures, such as, the static, let's say more or less static tables, the intermediate data results for the query execution, and then also secondary data structures such as indices and statistics. If you look at, the resource consumption, they are quite bursty. So on the one hand, you have transactions. On the other hand, you have very resource consuming analytics queries. This is here, this hybrid transaction processing. And especially with this analytical queries, you have significant intermediate memory usage. So for example, we first thought, this could be probably a good use case to say, if I have a very big join or several joins with huge intermediate memory usage, we can, let's say, spill over to other systems to use their main memory. And we also did some initial experiments with a typical benchmark in the database field. This is TPC-H, where we measure ThymesisFlow completely running on local memory and completely running on remote disaggregated ThymesisFlow memory. But first, let me say a few words on the setup. We basically built it with two IC922 machines and two Alpha Data 9v3 cards. These are connected to the OpenCAPI ports on the motherboard, so you also need OpenCAPI cables, of course. And these FPGA cards have on their back 100 gigabit of network ports, and so you also need cabling, and then connect them back to back, and then you can have a running setup. You also need some software for that, and this is, of course, this ThymesisFlow. There you get the let's say bit streams you flash on the FPGAs, and then you also have this ThymesisFlow agent, which you need to configure the FPGAs and allocate memory and share it basically between the two systems. And then the question is, okay, how do we actually get to use the memory in our applications? So there are basically two modes. First is we use a kernel module, which exposes our static offsets, and I come to that in a second, and presents it to us as a device which we can mmap. Or the other one is that we patch the firmware on one of the machines. For that, we use the ski boot and apply a patch. And this basically creates a virtual memory bar with a certain physical address in the device tree, and then Linux can use it as, let's say, normal memory. And I said with certain offsets and static offsets, basically depends where you connect your cards, as seen here. So in these IC922 systems, we have two processor sockets, and whether you connected the card to processor 0 or processor 1, it has a fixed static offset for which it listens basically to the load and store operations. Okay, so with all that software installed, how does our stack looks like? So on the memory node, we have a normal IC922 machine, a normal firmware, a normal kernel, just the checked out libThymesisFlow agent, and then we can, attach memory to a card which we have in our system. We specify that with this --AFU. We can have several, let's say, virtual channels. So we could share multiple memory regions with theoretically multiple systems, and we specify the memory size. On the borrower system, it depends if we want to have hot plug or this M-mappable memory. For the hot plug, we would need a modified firmware. For the M-mappable kernel module, we wouldn't need the firmware, so we could leave the vanilla firmware, but you would need the kernel module and the ThymesisFlow agent, and then we would, attach one compute node, which offers us the memory. And we also have to specify our effective address, which in essence configures this FPGA card as a memory translator, so that the addresses get translated to the virtual addresses of the other address space. Right. So when we do that, now we can go and write or modify an application to use that kind of memory. For example, let's say we want to do some latency measurements to see how far this memory is in terms of nanoseconds. So what we see here is on the right side, if we chose hot plugging and we examine our system topology with this NUMA control utility, then we see, okay, we have here now a NUMA node 16, and it has a size of 512 megabytes. So we hot plugged here memory to this node 16, and we can now use it like normally with malloc, and could allocate it specifically from node 16. The other one, if we chose to go the path of the M-mappable kernel module, we would insmod the kernel module and then basically do an mmap on this. So we open this device and then do an mmap with the size we want to need, with the size we need. So then, for example, let's write a simple pointer chasing workload where we say we have structs which are 128 byte aligned and padded. They are randomly shuffled, and we configure the total allocation size, and we configure ThymesisFlow, and then we start the application. And oh god, this will lead to a bus error. This, by the way, was also nearly one of the first impressions we got with ThymesisFlow. And the reason was, it's a research prototype, so don't expect it to run out of the box. But the thing here was that we should not have cabled it back to back. There were in the ThymesisFlow a hard-coded network cage. So they assumed a crossed connection, which we didn't know. And so, yeah, we just changed this 0x1 to 0x2, and then, it worked. So we could do some latency measurements. And with this pointer chasing workload, we discovered that we are round about at 854 nanoseconds. And this was kind of consistent up to 10 gigabytes. And then we noticed if we go to, 46 gigabytes, so rather big workload, we see a slight increase in the latency. We are in contact with the guys from ThymesisFlow. We have to figure out where. So if this is where do this come from? Okay. So let me quickly sum up. So the status of the current prototype, we have modifications on nearly every stack, on nearly every level of the stack: firmware, operating system, libraries, applications. We also did some changes ourselves, so it also extend what we got with ThymesisFlow. And we are currently in the progress to open source as much as possible, / creating pull requests, for example, for ThymesisFlow, where we extended it, for example, to work with shared memory segments, which we need for a demo later on. Okay, we also are in collaboration with other universities, for example, TU Delft, and there was an accelerated big data systems group led by Said Al-As, Peter Hofsti, and there, especially one of the PhD students, Akosh Hatnagi, he basically said, okay, for the setup, having two machines is perhaps not necessary if I could have one FPGA card serving two modes, these M1 and C1 modes, so having a loop back to ThymesisFlow. And we talked to them and said, okay, right, that's very interesting. What if we could also add another component where we could, inject configurable delays, so we could test workloads under different latencies and, answer questions like how far can data structures be placed in the data center if you think that you could, connect arbitrarily large number of machines with that technology. Okay, looking at the time, let me quickly get to the Hyrise experiments we've done. We did some experiments with this TPC-H benchmark, and this TPC-H benchmark has 22 different queries. What you see here is a comparison of the runtimes of a Hyrise running all the queries purely on local memory and one running purely on disaggregated memory. And the y-axis is the relative slowdown. We did that with a scale factor of 10, so you could think that you have roughly 10 gigabytes of table data, just to give you a size comparison. And so we see that, on the one hand, some queries are quite heavily impacted. So for example, query 9 runs 4.5 times slower on disaggregated memory than on local memory. On the other hand, we have, like, for example, query 1 or query 16, which are not that much impacted. So there, it doesn't make that much of a difference if we use this disaggregated memory. And so we're currently in the process of figuring out what's the reason for that. And perhaps I just very, very quickly give you a very short introduction to the way Hyrise and perhaps most in-memory databases are layouted. So we have different tables, and within the tables we store, our tuples not in a row fashion, but in a column fashion. So this is one thing to have in mind. The other one is, if we have intermediate results, let's say virtual tables, which we create throughout our operator chains, inside those tables, we will store position lists instead of the actual values. This is also called late materialization. Why? Because these value vectors are heavily compressed, and if we would copy them out, the values, we have to decompress them and they would need more memory. And so we just store these position lists. But this, in contrast, also means that if we have stored the table on remote memory with a high latency, and we have position lists, that we always, if we have to compare the values or search for values, we always access the table on the remote memory. So this is not a problem if we have, continuous memory accesses, because we could prefetch them and do all kinds of tricks. But if we don't have that, it will have a heavy cost. And this is currently our theory, why we see that some queries are more affected than others. So for example, this query 1, if you look at the operator tree, when you execute the SQL query, it's very linear, and we have here a table scan which searches for a ship date which is smaller than. So if you think that the values are most likely sorted by date, you will have a position list which is continually accessing the table, so which is probably very good prefetchable. Probably not so much on this query 9, which was heavily impacted. So we see that for the very expensive operators, we have inputs of another join hash where you have to materialize some stuff, and probably, so our theory is that here we have position lists which are scattered, not so good prefetchable, and we are thinking about, if that is true, if we could materialize meaning copying over the values before passing them on to the next operator, and see if we could solve at least some performance issues here. All right, and yeah, with that, let me hand over to Andreas Grapentin.
Thank you so much, Felix. Let me see if I can share the next part of the presentation really quickly. I think you need to stop share for that.
Yes.
Cool. All right, let's try this. I've never done this before. Can you see the slides?
Yes, we can see them.
Ah, perfect. Okay, thank you. So after Felix told you everything that we can already do and is kind of working, let me now talk about all the things we cannot currently do. And I think I started on the wrong slide. Hang on. Let's quickly move through this. You've all seen this already. Almost there. All right, because there's like a bunch of open questions that still need to be addressed in order for this to make any sense. And we've gathered these into 3 categories. First of all, you have to talk about performance, right? Because when you think about now you have 2 separate machines and you have byte addressable memory across machine boundaries, you have, of course, a large penalty in terms of latency, right? Because your memory is even further away than you're used to in large NUMA systems. And I'm getting into more detail a bit later. The next part is reliability, because now for the first time, really, you have byte addressable memory that lies beyond machine boundaries. You have new kinds of things that can go wrong and new kinds of ways it can go wrong, right? Maybe your ThymesisFlow agent on the other side of the on the other machine has just crashed and now your memory is no longer available, or your FPGA has failed. And but your process and your private memory is still fine. So how do you deal with that? Can you recover? Like, this is something that we look into. And also, of course, architecture. With these kinds of memory properties, right? Your memory is suddenly behaving in a way that you're very much not used to. And I'll go into more detail in a bit, but suffice to say at this point that your hardware architecture necessitates some ways, some change in the way you think about your software architecture. And we'll talk about this in a bit as well. But first, maybe performance. As you know, NUMA systems have this tricky property that not every address of memory has the same latency and throughput properties, because some memory, as you see here, there's this is a 4-socket system with a fully connected interconnect system, and each socket has its own attached memory, and these all share the same physical address space. So when you have your compute on this socket over here, and your memory is on this socket over here, then your access latency and throughput will be worse than, for example, if your memory was here, because you have to talk to this socket over here in order to get your data. That's not the whole story because of caches and stuff like this, but this is the gist of it, right? And there's this rule of thumb that your workload can be slowed down like a factor of 10 if you don't care about NUMA. And if we look at the disaggregated memory, you can now think about your system as having 2 of these and 2 FPGAs in between. So what you basically have is an even larger NUMA topology. And we're trying to coin the term super NUMA for this, but it hasn't really caught on yet. But this is basically what it is, right? You have NUMA on steroids, basically. So when you think about how to mitigate the performance impact of this distant memory access, there's plenty of related work in the field of NUMA optimization, right? So this stuff has a lot of synergy effects where you optimize for cache hits in order to mitigate the higher latencies. And this means you need to access your data patterns and avoid excessive pointer tracing, because pointer tracing, when your next memory access depends on the result of the previous one, you can imagine that this is very sensitive to latency increases. The next part, reliability, I teasered a bit of it. Now you have 2 full stacks of systems, and where you lend the memory to one, so your typically when you have a server system, if your memory fails, your SOL, you're shit out of luck, and your process basically is dead along with the whole system, right? Unless you're on a mainframe where there's a bit of redundancy here, but this is a different topic. But now you can have a memory region that you pretty much know exactly where it is and what you put there, in the best case, fail in an isolated fashion in a way that you can maybe tolerate this failure. And the question becomes, how do you deal with the failure then? Because if it can be tolerated, there should be ways to do it, right? And typically you would expect, we haven't really worked this out yet, but we would expect there the failure mode to be like the process receives a signal from the system, which is a SIG bus when it accesses the memory that is gone, right? And we also need to ask how we build a fault-tolerant operating systems with that knowledge. And the easy way out is, right, to put no kernel memory on the borrowed memory, right? And again, there's plenty of related work here when you look at how distributed systems work to try and figure these things out. And the next part, and maybe the most important one that has impact on the other two I discussed, your architecture. And this is twofold. This is software and hardware architecture related. Because when you have this heterogeneous memory layout, there's also plenty of related work. You can look at the scope of volatile versus non-volatile memory, local versus remote memory. You will always have memory that has different functional and non-functional properties, and also different reliability, which ties in to what we said before. And especially when you look at the disaggregated memory, you can imagine two different ways of using it, right? You can use it privately, where you get it from the loaner only for your personal use. For example, as a simple extension to your physical memory, where you just look at how can I fit my scale-up workload that's larger than my personal system in my available memory, right? So it's capacity oriented. Now the other side, you can look at it as a way of distributing a memory in order to compute on it on different machines, right? So you're data flow oriented and look at if I collaborate on this memory, what do I need to place where? Where's my workload? Where's my memory in order for my application to work as efficiently as possible? And an example here could be the database we discussed before, Hyrise, deployed in a distributed way, but still able to access shared memory, which is kind of interesting. So we're having this concept of loosely coupled shared memory here. Okay, the question here becomes, how do we manage abstractions from the operating system, because you want to avoid rewriting applications, ideally. And one idea here is have memory pools, right? You have memory with different properties, and a very easy idea is then to not mix allocations through these pools, right? You have memory you want to place here, and you want to have it placed there, so you need two heaps to separate them. And oh, and one more thing that's just right at the bottom here. It's hidden by my bar, so I can't see it, but you can see it. For the first time, I think we are now able to have shared memory systems where the participating compute units can have different instruction set architectures. So for example, we can connect, but we could theoretically connect, we can't do it yet, but we might look into it. We could connect the power system that is running the memory inception or the memory inception prototype, ThymesisFlow, with, for example, an ARM board or RISC-V or something like that as an accelerator kind of thing, right? And then have shared memory access between these two machines, which is kind of crazy. Okay, I talked about different heaps. What is a heap? I think you all know what a heap is, but why would we need separate heaps? If you look at how C++ and C also manages memory, then you have objects and in C++ and standard allocations in C. When you have your data structure, it's basically not one block of memory, but several which are linked by pointers. And you want these grouped by their properties, right? You don't want these mixed and then have to decide, okay, I have my page where my object is stored, but in reality you have 5 pages where the mixed data of 8 objects is stored, and you want to move one object away, then you run into something what's called fault sharing. So instead, what we have is we have a prototype called Pegasus. The similarity in name to Pegas is not a coincidence, right? Partition global address space, you might know the concept. Where we say, okay, we have multiple heaps, data sources basically, which are managed by a standard allocation algorithm like ptmalloc or dlmalloc was the other one, I think. And then you can say, okay, for the next allocations, I want everything served from the heap that is on node 5, for example. And then you can be sure that your data is where you expect it to be. And there's also a bit more behind the scenes. There's NumeraWare data structures and a tasking framework behind it that you can easily spawn your work near your data where you want it. And there's also the concept of stacked allocations, which might make more sense. I'm running out of time, I'm sorry. Which might make more sense if we look at this. This is an allocation flame graph. To put it simply, every time, if every time you allocate memory in your application, you take a snapshot of your stack trace. And then afterwards, you analyze it, you can build a graph visualizing where in your application you allocate how much memory. And this is what you see here, right? This is, I think it was a run of the Hyrise database again. And you can see, okay, we have this initialization period here, and then we allocate table data, then we prune it again, and then we calculate a histogram. And in essence, what you can then do is, you're using Pegasus, you place a guard, which means, okay, following all allocations until the guard goes out of scope and gets deallocated, will be served from the memory on, in this case, the memory source on the current node. So using this, you have an easy way of distributing the memory where you need it to go, which is kind of cool. And this is what we intend to, like, linking back to the questions I started with, this is a way to deal with the increased complexity of memory allocations on the disaggregated memory. And having said all of that, there's a bit more time for one concrete example project that we are looking at, and this is by Tobias Sagoni. Tobias is one of the master students in our group, and he's done excellent work. And that I think he will now present himself. So I'll stop the share.
Can you show the
hand over to him.
diagram?
Oh yeah, I will show that. And I think you need to speak up a little. You're very quiet.
Okay. Yeah. Let's have a look at what we are doing now. Essentially, we are doing a normal live migration of a virtual machine running in QEMU with accelerated with KVM. But instead of doing it normally with a clever mechanism that ensures that tries to move the right pages at the right time, we will use ThymesisFlow, and we will just move the execution to a different machine connected with ThymesisFlow without actually having to move all the memory. And now we can quickly have a look at this diagram, how ThymesisFlow is set up. We have two machines. This is the O3 and O4 machine. On the left side, we see as a machine where our VM was first started and is now migrated away. It has the pages we use in physical memory, and it's running the ThymesisFlow agent, which was modified to use a shared memory segment, so it could use these pages. So it has these pages mapped, which were the same pages also QEMU had mapped in the past, but QEMU is migrated and it's running on the other machine. And here we see this machine has the same amount of normal RAM, but in its physical address space, it also has the remote mapping, which is essentially the virtual address space of the ThymesisFlow agent on the source machine, and QEMU is running there using the pages transparently. So I think now you can stop the screen share and we'll watch a short video how it looks like currently. So what are we seeing here? We are seeing two VNC sessions. On the left hand is our source instance of QEMU, which runs just like any normal KVM virtual machine on the source machine at this point, and we want to migrate it away to the right side, which is currently waiting for an incoming migration. And just have a look at it. Of course, it's a Power PC because it's running on the ThymesisFlow prototype, and we are just using it normally. And now we will start a video on it. And here we are connected to QEMU's monitor console, where we trigger a migration to the other machine, which is connected via ThymesisFlow, and we see pretty much instantly the execution continues there. And what we can't see here, but maybe we see it because how quickly the migration happened, it is using the remote memory, and it didn't have to transfer any memory before continuing to execute on the other machine.
All right, thank you, Tobias. Then I think also the time is up. Perhaps just a little bit of advertisement, because we're also organizing a workshop hosted at the IPDPS. It's called the Composable Systems, and it's about the topic we just presented, all kinds of memory disaggregation. So you know, if you have something to contribute, a paper or you know, a talk, just get in touch with us, or you know, you have here the URL, and yeah, all right, that's it. Thank you. Now I think perhaps we could answer a question or so, if there is one.
There is one question from Stefan. I don't know if you can see it. I will just say it. Was the VM migration demo using PGA SUS?
Pegasus, yeah. Tobias, you want to answer?
Oh, it doesn't. Simple answer.
So I think the question...
Maybe as a further explanation, I think Pegasus was more about optimizing software and using the different types of memory in an efficient way. And what we did here was a bit of the opposite. We just like to move around entire VMs naively and yeah, put the whole operating system in remote memory.
Felix, I think the next one is for you.
Yes, I see it. I just skipped to slide 16 to share it. All right, so question 16, latency versus bandwidth impact. Oh, and thank you. So this is done single-threaded, so we didn't we didn't exceeded the bandwidth limits ThymesisFlow offers us. I think it's around 10 gigabytes, and with a single thread, I think we don't come near that border. So for these workloads we see here, this is purely the increase in latency, which impacts.
We're looking into doing benchmarks from within the virtual machines, maybe, because as soon as the machine is running remotely, accessing the remote memory, you can start running stream benchmarks and try to get a feeling of the bandwidth limitations. But this is still in the planning phase, so we haven't done this actually yet. But this is something we're going to do in the next couple of weeks, probably. Or something smarter, if you get a better idea.
All right, I think then we don't want to delay the next talk by that much, so I think then we're finished.
Yeah.